Welcome us to another applied regression analysis class. I want to believe those of you at the back, you can hear me clearly, right? Okay, thank you so much. Oh, you can hear me. Uh, Okay. So what about now? You can hear me clearly? Okay, thank you so much. Okay, so like I said, once again, I want to welcome you to another applied regression class. Before now, I think I've been posting my recordings. I remember I posted 2 recordings last night on the variable selection and shrinkage. And of course, this is also being recorded. Okay, so and I think I've also published all the remainder, the materials, the outstanding materials for the semester. You can check the canvas in case you actually want to read ahead of time. So I want to welcome you into another statistical topic that we'll call non-linear regression. Of course, all this why we've been actually looking into relationship between the response variable and the predictor, putting into consideration the linear combination of regression parameters. But what we're going to be doing from now, okay, is not going to involve linear combination of parameter. Instead, it's going to be nonlinear. Okay, so in the outline, I'm actually going to introduce you to nonlinear model. And of course, we have 2 types of nonlinear model. So I'll make a distinction between intrinsically linear model and intrinsically nonlinear. And of course, I'm going to walk you through some examples of both intrinsically linear and intrinsically nonlinear models that we have in statistical literature. And of course, the same way that we make comparison under linear models where we actually make comparison of nested linear models. I'm also going to walk you through how we can actually do the same with the non-linear models. Okay, so please pay attention in case you need clarification. And of course, I need you to ask questions. Okay, so I want to start with the introduction. Okay, you know, um, like I said, in the linear models that we've done before, we are actually seeking linear relationship between variables. There's possibility that that kind of linear relationship may not exist. Okay, and what we actually gonna have is non-linear. Okay, so and that's why here I'm actually seeing a nonlinear regression model as a generalization of the linear model. Of course, the conditional mean function that we have before is not going to be a linear one. Of course, the way we normally write the estimated mean function under linear relationship, that's going to be linear in parameters, but in the case of nonlinear, we actually going to be looking into the generalization. Okay, so I'm gonna do this. I'll first make a distinction. There are 2 types of. Now you understand what I mean by nonlinear model. Of course, by nonlinear model, we actually mean that the relationship between the variables are no longer linear, and of course, we're not going to have linear in parameters. We're going to have a nonlinear in parameters. So there are 2 types of linear mode nonlinear models. Okay, I'm going to say that again. We got 2 types of nonlinear model. We got intrinsically linear model. We got intrinsically non-linear model. What do I mean by intrinsically linear model? Of course, intrinsically linear model means I have a non-linear function, but after performing algebraic transformation, maybe I found a log, or I find a square root or reciprocal or any transformation that you have learned in the course, and you realize that it now become linear. I'm going to say that again. Right now, I want to differentiate between intrinsically linear and intrinsically nonlinear. The intrinsically linear and intrinsically nonlinear, they are types of nonlinear model. Okay, so the intrinsically linear means I have originally I have a nonlinear model, but after performing algebraic transformation, of course, the transformation you've done before in this course, maybe logarithmic transformation, or the square root transformation, or reciprocal transformation, and so on like that. And you are now able to linearize that. If you're able to linearize that, then it become what I call intrinsically linear model. So if you're able to linearize that, of course, it means you can use the conventional approach that we use in linear model. Okay. But what about intrinsically non-linear? Originally, it is non-linear. And when I try my effort to make sure it become linear, no any form of if intervention that make it linear, then in that situation, I'm actually going to call that intrinsically non-linear. Okay, it is non-linear, but I try to transform the model, but no matter the effort, okay, the model remain non-linear. Okay, we call that intrinsically non-linear. No situation where you have intrinsically non-linear model, then what we're going to do, we can't use the approach of linear model. What we're going to do is actually to go by iterative approach. I'm going to say that again. The moment it is intrinsically nonlinear model, okay, I'm actually going to use iterative approach. I could use iterative approach like Newton-Raphson. Has anybody heard about Newton-Raphson? Okay, so we're going to use iterative procedure. We're actually going to start with a very good initial guess, for us to have a faster, convergence, okay, because that will depend on your initial guess. Okay, so I'm going to show you some different kind of models, this one that can be classified as intrinsically linear, and this one that can be classified as intrinsically nonlinear. Okay, so if you take a look at, give me 1 second. If you take a look at this guy here, okay, of course, this may be, this is linear. Okay, it is linear in parameter. Okay, even though it is non-linear in variable, that's okay. Okay, so if it is linear in parameter, we can still apply the method of a linear model. Okay, I wanted to take a look at this. This is looking non-linear, but after taking the log, I got this guy. Oh my God. When you take a look at this guy now, this is now become linear. Okay, because it is additive in nature now. I can actually call my log of y to be maybe y star. I can then, I can call my the natural log of S2 to just be S2 star. I can call the natural log of S3 to be S3 star. Of course, here, if I want to estimate the parameters in this model, I'm still going to use the conventional approach for linear model. So I think I'm trying to give you an example of intrinsically linear model. Okay, the intrinsically linear model is a type of non-linear model. Okay, originally they were non-linear, but after algebraic transformation, they become linear. Okay, so that is intrinsically linear, like I said, but I needed to pay attention to these two models. No matter the efforts, they're never going to be linear. Some of you may be wondering, I just need to take a look at this guy and this guy, even though they are both called Douglas equation, but the error enters here. UI is the error. Error enters here multiplicatively. If I actually take the log of that, it's gonna be additive. But when you take a look at the one here, error enters this model additively. If I take the log, okay, this cannot be linearized. So this will actually fall under, non, other intrinsically nonlinear model. And of course, this guy here. Okay, if you take a look at this model, of course, that's also an example of intrinsically nonlinear model. Let me tell you this. When you're working with models, for you to be able to know the appropriate statistical method that you actually going to use in the estimation of parameters in that model, you need to be able to understand whether your model is linear or whether your model is nonlinear. And if your model is nonlinear, can I have a way to transform the model? If the model is transformed algebraically and it become linear, it means you can still use a linear approach to estimate the parameter. But in a situation where you make an effort, to linearize that, and if it's an exercise in futility, of course, you're actually going to go iterative way, to figure out the parameters in the model. Okay, so these are other examples of that. Now, I want us to visit some models that we know in real life. Okay, I want us to visit the models that we know in real life. I want to talk about logistic growth model. Has anybody seen this model before? Okay, logistical growth model is a very good model. If I actually want to estimate the population of a country, or maybe I actually want to figure out maybe during the epidemics, okay, maybe during pandemic, I actually want to know the number of positive cases of a disease, and stuff like that. So this is a non-linear model. If you take a look at that, I have three form of parameter here. The theta one, the theta two, the theta three. And of course, if you take a look at the theta one is here is looking like a carrying capacity. Okay, this is a logistic model. The theta one is like a carrying capacity. Of course, you have the theta three here is like a growth rate. Okay, take a look at that. The theta three here is actually like a growth rate, and of course, the theta two could shift the curve to the right or to the left. So I just wanted to take note of that. It's an example of nonlinear model. Now the question now is, I got a nonlinear model, and I want to figure this out. Because if I decide to go by way of a transformation now, there's possibility this is not going to be transformed linearly, which means I may not be able to use the linear approach of seeking redress. So what am I going to do? Of course, I'm actually going to use an iterative procedure. I want to figure out what is the theta 1, what is the theta 2, what is the theta 3. Those are the parameters in this model. Okay, then I'm actually going to use non-linear least square. Of course, under the when we're dealing with a linear relationship, we use ordinary least squared. Ordinary least square is applicable to linear relationship, to straight line relationship, but situation where I got non-linear, of course, we have a non-linear least square. Okay, so when I have a nonlinear least square, then of course the same way that I minimize the error, okay, the same way we minimize the error in the using the least square, we're also going to minimize the error in the nonlinear least square. Of course, why am I minimizing the error? Because the growth model, if you look at the specification of this model, there's also an error in the model. And let me tell you this reason why statistics is very attractive, why statistics is a worthwhile is because of the fact that because of the inclusion of the error in the model, then we are actually able to know how we can validate the model because there's no error. There's no way we can validate the model because you can validate the model. if the error exists, because there's going to be assumptions. Assumptions will rely around the error. And of course, if the assumptions look great, of course, we expect the model to perform excellently. Okay, now I need you to pay attention now. You know, when you take a look at this model now, the model that I just talked about, okay, if you want to, when we try to make an attempt, if I don't want to solve this model directly, maybe I want to try and see how I can linearize that, okay, but I'm going to tell you this. If y equal to this, okay, when I decide to simplify in such a way that I actually want to have a linear combination of parameter. Okay, that is not going to be, let me just say, possible 100%. If you take a look at what I've done, mathematically, when I go from there to there, that is what I'm actually going to get. Even though I'm having a linear relationship here, but you know what? The parameter theta one is also part of this guy. And that is the reason why it is better. But why am I doing this? Why am I actually doing this? Let me tell you this. The essence of doing this is just to be able to achieve two things. And I need you to pay attention and get the information. The very first thing why I'm doing that, just want to try if algebraic transformation is going to work. If I'm actually, after transforming that, okay, if that is going to be linear in parameter, because the moment it is linear in parameter, it's going to be easy figuring out the parameter, because a linear approach is the most simplest approach ever. Okay, so that is number one thing. But at the end of the day, I realized that, that cannot be completely linearized, even though we have a theta 2, theta 3 at the right hand side that is having a linear relationship. But look at the left hand side. Another reason why I need this, I'm going to tell you now. Even though, okay, if I've done this now, and this is how far I can go, and the transformation is not going to yield, intrinsically linear, okay, and the approach is only going to be intrinsically nonlinear, which means if I want to estimate parameter, I'm actually going to use nonlinear least square. But for me to use a nonlinear least square, I need a very good initial guess. I need initial guess for theta 1. I need an initial guess for theta 2. I need initial guess for theta 3. If I just choose initial guess arbitrarily, of course, my iteration may not converge. So what do I need to do? Do you know, with what I've done here, I can have a good sense of what the theta 2 and theta 3 is going to be. If I try to, if you take a look at the whole of this guy, if I call the whole of this guy a variable, maybe y star, okay, that will become a log of y star equal to, that is looking like a log linear model. And in this situation, I will be able to estimate my theta 2 and theta 3 using the linear regression approach. And finally, I will be able to estimate my theta 1. But the theta 1, the theta 2 and theta 3 that I'm actually want to get from here, I want to use them as an initial guess in the iterative procedure. I'm going to repeat that. We don't just choose initial guess arbitrarily. We want to have a good sense of initial value for the model to converge to true value. Otherwise, the model is going to diverge. We don't want that. Okay. And a good sense is through this through the transformation I've done, I can, apply a linear regression to obtain the theta 2, theta 3. And after obtaining the theta 2 and theta 3, I can get theta 1. The three value that I got will serve as initial value in the iterative process. Now, I need you to pay attention now. I want to apply this to United States population. I told you the logistic model, the nonlinear model, naturally be used to estimate, to predict what the population is going to be. in a particular year. Now, if you want to have access to this data set, of course, you're going to load a library, or you need to have a load a package called car and data US population. And of course, I want to use, you see, my Y is population, and this is the model, right? This is logistic model. Okay, let's say I did not really know the initial value, but there's one initial value that is very, very crucial. Please pay attention. Okay, it's actually the theta one. It's actually the theta one. In a logistic regression model, the theta one is a carrying capacity. I will look into the data. I will choose a reasonable value. Of course, the population of the United States probably between 350 for 400 million. I can just choose 400 as in, that's why you see 400 here. Okay, logit. Here I say formula logit, population divided by 400. You know what oh my God. Do you know what I'm trying to do here? Please pay attention. Are you ready? Because it's getting serious, getting complicated, and I need you to pay attention. Do you know what I'm doing in this page? What I'm actually doing in this page? I just want to obtain the initial values. I've not even started, but there are three parameters. The theta 1, theta 2, theta 3. But do you know I coded this based on this guy here. You know what I want to do here? Okay, before moving forward here now, I need to know the value of theta 1. In my data, I have Y in my data, right? I have Y in my data. Okay. If I assume a value for theta 1, which is the carrying capacity now, which I choose to be 400. Now, log of this is like an odd ratio. Y over theta 1 divided by 1 minus Y over theta 1. If I have a log of odd ratio, that's a logit in statistics. Now, that's what I'm trying to specify here. Take a look at that. When I say logit, population over 400, it means log population over 400 divided by 1 minus population over 400, which is this guy here. Please pay attention. I'm trying to do this. I'm trying to apply this. Okay. I have to know theta 1 before I can use ordinary least square to obtain the theta 2 and theta 3. After getting theta 1, theta 2, theta 3, okay. Now here, you know what this guy is telling me? It's here, oh, theta 1 is 400, theta 2 is this one, theta 3 is this one. Oh my God. Those are the three values that I'm actually going to use in my iterative process. Now I want to specify them now. I want to go into nonlinear regression. Take a look at that. If you take a look at this guy now, hold on 1 second. Okay, so if you take a look at this guy, I now want to use them now. Okay, these values and these values are the one that I got. Now, in the non look at NLS, non-linear least squared population. I will state the model. Then I will start a list of initial value. The 400, the theta 2, the theta 3 that I estimated initially. Then I'm gonna run that. Okay, this is what I'm actually gonna have. What is the first? What do you see in the first column here? Please pay attention. The first column here represents residual sum of square. Now the residual sum of square is and here is the theta 1 initial value for the theta 1, initial value for the theta 2, initial value for the theta 3. This is showing us the iterative process. This is actually saying, oh, there's a drop in the residual sum of square and it gets to a point, it converges. When the residual sum of square start dropping and it converges, then the parameter will convert to true value, which means the 400 will convert to true value. This guy is going to convert to true value, and that guy is going to convert to true value. And that's exactly what we have right now. And that is how we actually estimate the parameter from, using the non-linear least square. Okay, now, if I want to know whether the parameter estimated as statistically significant, that is what I'm just going to say summary of pop dot, summary of this guy here. Okay, a summary of that, that's going to give me, I'm actually going to have the opportunity to know how significant or the estimated parameters in the logistical model. Does that make sense? Okay. And, and
Right.
of course, I'm actually going to say the estimated upper bound for the US population is just 440, 440.8. Where do I see 440.8? Okay, right here, the last value. Okay, which is like 441. That would be the estimation. Okay, so take a look at that. Okay, so that's exactly what I have. Okay, I want to go into another model, but this time around, I want to talk about intrinsically linear model. And one of them is Macaulay-Menten model. Has anybody heard about Macaulay-Menten model? It's an intrinsically linear model. Okay, the model is actually this: y on s. This is not linear. Okay, so what we're going to do? We actually want to transform this model. Okay, so if I have 1 over y, I'm actually going to switch this. When I switch this, I'm actually going to benefit from algebra. K divided by that, x divided by that. Can you see that now? When I have this guy now, s cancel s, I'm actually going to have this. So 1 over y equal to this. Okay, so from there, I'm actually, now when you take a look at this now, I can boastfully write this as a linear model now, even though I started nonlinear. Okay, of course, 1 over y, I can call that y star. And of course, this guy is going to be the beta naught. And if you take a look at what I have here, this guy here is actually going to be the beta 1. Okay, as I see this guy now. Okay, and of course, so I have all of that and k equal to that. So what I'm actually going to do here, okay, I'm actually going to run a linear regression model, and after getting my, for instance, if I get my beta naught, okay, how do I get my VM? VM is the original parameter in the model. If I get my beta naught, then my VM is going to be 1 over beta naught. If I want to use that relationship now. And if I get my beta 1, I can figure out the K and VM. You know, the K is ratio of beta naught over beta naught. You can see the way we're actually figuring out the parameter in the model indirectly, okay, by way of the transformation, okay. So I'm actually going to show you how this is done in R. Now, Macaulay-Menten model is it can actually be applied in a chemical reaction. Is anybody here from maybe chemistry or any chemical engineering or anything that has to do? Okay, so thank you so much. Maybe I actually want to look at the relationship. I want to believe a non-linear relationship exists between concentration and rate. Probably maybe the rate of reaction and the concentration. And of course, you can see when I sketch a plot, you can see it's a curve. It's not linear. Now, in this situation now, okay, what am I going to do first? Okay, I need to, if you go back into make, if you go into this, I'm actually going to program that. I'm going to show you how to do that in R. That's what I'm doing here. Okay, 1 second. That's exactly what I'm doing here. Okay, that's what I'm doing here. With that, I'm going to get my VM. I'm actually going to get K. Okay, now let me tell you this. If I'm able to transform a model and it is non-linear and achieve linearity, we don't normally say that is the final answer. Of course, we can actually going to say the values that gave us is an initial guess. I'm actually going to call that initial intelligent guess. Okay, that I can use in nonlinear or least square. Now I got VM and this parameter, they're gonna be the initial value after transforming, because without transforming, I may not be able to estimate them using a linear model. It's like I'm estimating initial guess using a linear model, and uh, you know back to the nonlinear, where I'm actually want to use them as initial guess. Can you see that? That's exactly what I'm doing now. Okay, so take a look at that. And when I use it, this is what I'm going to have. Can you see that? Okay, like I said initially, here, this is actually the residual sum of square that is actually going down, and these are the parameter. Of course, we believe it's converged. The two of them converge. Let me tell you this: at times it could take forever if you did not linearize first. If you have the model and you did not actually go by way of this to linearize to be able to know how to estimate the very sensible intelligent guess. If you just choose if you just choose your initial guess arbitrarily, your convergence will take forever. Does that make sense? Okay, and we don't want it to take forever. So that is the final result. Okay, so this is the model. After fitting the model, okay, you can see it capture the reality. Okay, so take a look at that. So, and that was why I said we model the relationship between variable using the market list matching model. And of course, you can see before first figure out, for first linearize, to be able to estimate the parameter, to have an initial guess of those parameter. And after that, we proceeded to the non-linear least squared, and we use them as initial guess. Okay, so that was the final result I will get for K and VM, because let me tell you this. Uh, we need K and VM. If you take a look at the model, okay, if you take a look at the model, if Y is concentration, okay, if I have a Y and S where one is concentration and the other one is rate, if I want to relate concentration with rate, then I need to have estimated the VM and K, which is what we've already done. Without estimating the parameter, there is no way I will be able to, explain, I will be able to have a sense of the relationship. Okay, and in the iteration process, okay, we can use a Gauss-Newton, we can use a Newton-Raphson, and so on like that. I actually want to move right now, and I need you to pay attention. This is very, very crucial. I'm actually interested in the weight gain and the amount, the percent of diet. Okay, you're looking at the effects of diet on the weight gain. Okay, now when you take a look at what I have here, okay, this is a nonlinear, right? It's a nonlinear. Okay, how many parameters do I have? I got theta 1, theta 2, theta 3. Okay, I want to perform this is a code in R. If I actually want to perform the nonlinear least square, but here I've chosen the initial value. You have to choose your initial value. They have to be reasonable. Otherwise, they're going to take forever. Okay, so when I run this guy, I got this guy. Take a look at that. This is what I got. Okay, so this is telling me, oh, this is theta 1, theta 2, theta 3, and of course, the p-value is actually telling me each of that is significant. And in fact, the arrow is going to report the number of iteration before it converges. But when you don't actually consider a very reasonable initial guess, the number of iteration for this to converge may take forever. Okay, this is the plot. Okay, weight gain against the percent of diet. You can see that's non-linear. That's actually non-linear. But there's something I need you to see. Please pay attention. Please pay attention. When you take a look at the percent of diet, I'm looking at the effect of percent of diet on the weight gain. And let me tell you this. I use a nonlinear model. This is a nonlinear model. Okay. And I want to see If I don't want to use a nonlinear model, if the weight gain can be categorized, I'm going to say that again. If the weight, because the weight, oh, sorry, not the weight gain, sorry. If the percent of maybe the percent of protein can be categorized, maybe I have a categorical predictor. Okay, maybe low values of protein, middle value of protein, the highest value of protein, which means I'm actually categorizing the protein into three different classes, and I want to look at the effects of the categorical predictor on a response. Of course, I'm going to use analysis of variance. Does that make sense? I will use analysis of variance for that. Now, let me tell you this. M1 here is using analysis of variance because that diet is categorical. That was why you see AS dot factor. Okay, now the name of my data is talk 0. Okay, now if I fit M1 here, if I is the analysis of variance model. Analysis of variance model is linear, not it is linear. Does that make sense? Analysis of variance model is linear in parameter. But the one we fitted before, this guy, is non-linear. Do you now know what I want to do? And I want to see, I want to compare both linear and non-linear. I want to see the one that make more sense. Okay, should I use just non-linear, or I should use analysis of variance that assume linearity? If I'm going to do that, that is exactly what I'm doing here. Please pay attention. That's what I'm doing here. And at the end of the day, I got this p-value. Okay, let me tell you this. Situation where you are comparing between linear and non-linear. Okay, in the non-hypothesis is going to be linear. The alternative is going to be non-linear. Now, what happened to the p-value? Now, the p-value here is greater than 0.05, which means I'm actually going to fail to reject the non-hypothesis, which means I do not need complicated model. Linear model can solve the problem. The linear model, the analysis of variance model can solve the problem. That is what this guy is trying to say. Let me tell you this. Uh, I want to use one example. Let me see. Okay, I'm gonna use this. There's a mosquito here, right? The mosquito is disturbing me. Okay, and I use a gun to kill mosquito. That doesn't make sense. Even if the mosquito is going to die, why am I using complicated? Maybe I can just use spray. Okay, situation where the linear model is going to work. Why are you wasting your time using complicated model? But I'm not going to. I can't decide on that. I want statistics to decide for me, and that's exactly what I'm doing here. Does that make sense? Now I want to go into the second half of the of our class today. In this class, we have compared nested models, nested linear models. Can we also compare nested non-linear models? And the answer is yes. We can actually do that. Let's take a look at number one. Please pay attention. Number one, the first model that I want to consider is what I call a fully group specific model. You know, I have three classes of protein, and the response variable is the weight gain. Now, this guy is trying to say I should fit non-linear model to each class. Can you see that? He's saying I should fit non-linear model to each class. Now, it means each class will have their own baseline. Then we have their own asymptote. Then we have their own growth rate. This is complicated. This is the most complicated model, but we don't know whether it's going to work. Let's put that one aside. I want to go to the second model. Please pay attention, because when in model building, we normally exploit different models to know the one that will best answer the practical problem. Okay, we have the practical that we address the practical question. You don't just go into a research. You have a practical question that you want to provide an answer to, and you need to explore. Now, let's take a look at the second model. The second model is trying to say, okay, let us build a model. Let all the classes of protein have the same baseline. You can see that? the Aushia theta 1. That is why we call that common intercept model. But they are differ in other parameter. Okay, they have different asymptote, they have different growth rates, but they only have common intercept. That is the second model. The third model, now, okay, can we consider situation where they have both common intercept and common asymptotes? But the only thing that will be different here is just the growth rate. This is another model. Okay, now the last model is a conventional model that we normally fit. This is a conventional one that we normally fit. We believe that all the classes of protein have the same intercept, they have the same growth rate, they have the same asymptote, and so on like that, which means no group differences occur. That is for this one. So I got 4 models now. Now I want to write the coding out for each of the model. That's what you see here. My TA is going to walk you through this. Okay. And then this is the code for each of the model. And when the code for each of the model will involve that you have to indicate initial value that's going to work on each of them. Okay. That is the code for that. But you know what I want to do here? That is a way to compare a nested models. I actually want to see, I'm considering M4, M2, M1. What are my M4, M2, M1? Okay, M4, M2, M1, M4. I want to compare this, okay, with that and with that. And let's see results. Please pay attention. Okay, this is going to give you this result. And I need you to pay attention now. Okay, do you know that the first one here will be the most simplest model, followed by this? This is going to be the most complicated. Let's take a look at that. I said M4 is the most simplest. Yes, this is the most simplest. Can you see that? Okay, take a look at that. M4 is the most simplest, followed by M2. Now I'm going to show you. Do you see M2? Then, then followed by M1. Let's take a look at the M1. Oh my God. The M1 is the most complicated. Can you see that? Now, if you now take a look at this, the first p-value here actually compare M4, it compare M4 with M2. Okay? Now, because the p-value is 0.27, okay? When I'm comparing M4 with M2 in the non-hypothesis, it's going to say M4. In the non-hypothesis, we normally have the simplest model. In the alternative, we're going to have the complicated model. Now, we're not able to reject M4 here because comparing M4 with M2, okay, the p-value is greater than 0.5. It's saying M4 is better. Then I'm going to compare M4 with the next one, okay, with the next one, and M4 is still better. Okay, when M4 is better, you know what it's trying to tell me? It's trying to say, oh my God, if you take a look at the M4, it's trying to say, don't waste your time. Just fit a nonlinear model where we're going to assume all the classes of protein, we have the same intercept, that we have the same asymptote, and then we have the same growth rate. That's what the guy is talking about. Okay, so I think I put the interpretation here. That was how I look at my conclusion. Okay, I said none of the more complex models significantly improve fit related to simpler one than the model with 3 parameter. Which one is a model with 3 parameter? Okay, the one with the 3 parameter, this one, the most simplest model, actually work because the p-value is greater than the 0.05 level of significance. Okay, now let's take a look at another one. Now, this is the second comparison. Okay, and we want to compare M4 with M3 with M1. Okay, and I'm trying to let you know M4. This is for M4. This is for M3. This is for M1. Okay, and at the end of the day, what you see is that the p-value is actually greater than 0.05. Then you do not need a complicated non-linear model because it's actually going to take you resources to figure out the parameter in a complicated non-linear relationship. So if that is not able to capture the fit, why am I wasting my time? Okay, why not settle for the simpler model? And that was why you see this interpretation. I said across all comparison, the more complex nonlinear model did not provide a statistically significant improvement over the simpler baseline model. So based on parsimony and ANOVA result, model 1 remained the preferred model. If you take a look at all what we have done. Now let me tell you this. We don't play to gallery in statistics. Maybe somebody that's supposed, or maybe they playing the game of soccer, right? Oh, sorry. Let me use basketball. Okay, you just dribbling and dribbling and dribbling and dribbling. Make a basket. But what they want is make a basket, man. So you just dribbling around and dribbling around and dribbling. That's like a playing to gallery. If the coach is not going to be happy, the supporter will not be happy. So we don't just choose model because the model is complicated. And we don't settle for simple model because of simplicity. We actually allow the statistical test. We rely solely on statistical tests to be able to figure it out. The next, what I'm going to walk you through next is actually called von Bartalaffi growth model. The von Bartalaffi growth model is actually one of the nonlinear models. And let me tell you this. Before I go, I've started. I think I've already, stop assignment. There's not going to be any new assignment for the remainder of the semester because I want you to concentrate on your practical assignment and I also want you to concentrate on your final. Okay, there's no any new assignment. And of course, don't forget on November 24 is the midterm. We're having that on Monday, of course, according to what we have in the syllabus. And of course, I think on Friday, I will briefly, maybe for 10 minutes before I start the lecture for Friday, I'm actually going to walk you through practice question. But let me tell you this, you all know what is coming. You need her. You need to come to this class with your laptop. You need her for that exam. So, this is how it's going to be done. So if I ask you to, maybe for instance, I say, okay, run this relationship, provide the mean function, stuff like that. Then you run it to your R, then you just write the number down on your exam booklet. But I'm going to demonstrate that with you on Friday. It's going to be so easy. But I will advise that based on the practice question that you have, start using R. You're actually going to use R, for that very exam. And let me say this, the final exam is not cumulative. This is the way I'm actually going to do it. The area we're doing newly, okay, the area that we actually doing after the midterm. If you take a look at the practice question in the midterm, of course, all those area in the practice question. I mean, the one for the midterm one, the one for the midterm two, will not be part of the final. So, which means what we are doing lately, okay, is very, very crucial when it comes to final exam. We have started strongly, and I want us to finish strongly. Is there any question before I go today? Okay, in the absence of question, make sure you all stay safe and have a lovely day. Bye for now, everyone.